Just as we have forces of attraction between atoms within a compound forming ionic or covalent bonds, we also have forces of attraction between individual molecules. And this is what holds molecules together into the three familiar states: solid, liquid, and the gaseous state. Actually, the forces we're talking about are going to be holding the molecules together in two of these three states, the solid and the liquid state. Because in the gaseous state, the individual molecules have so much kinetic energy that they're able to overcome these weak forces and move about totally independent of one another. So when we think about the forces that hold the particles together in a rigid crystalline lattice structure, as in a solid, or in a more fluid, slightly more freedom of movement mode in the liquid state, where the particles are held together within a specific region of the container, but they are free to move and slip and slide past one another. These forces of attraction are referred to as van der Waals forces, named after the Dutch chemist Johannes van der Waals. We call them VDFs, or I'll refer to them as by VDFs for short. When we talk about these different kinds of forces that we have the difference between intramolecular forces and intermolecular forces. And the difference lies, if you look at the prefixes, the prefix intra is talking about forces within a molecule. And so these would be, for example, covalent bonding forces. If we are talking about intermolecular forces, inter means between. So when you think about the interstate highway system, like Interstate 80 travels between states. When we talk about intermolecular forces, these are forces that are occurring between molecules. And an example of these would be these van der Waals weak forces. Now there are three types of van der Waals interactions that we'll discuss here. And the first one is, of the weak forces, of these van der Waals weak forces, they're the strongest. And so these are referred to as dipole-dipole forces. Now, dipole, if you recall, is a term that is used to refer to a polar covalent molecule, or a molecule that has polarity to it. And polarity of a molecule is determined by the polarity of the bonds and also the molecular shape. And so when we refer to a dipole, we are talking about a molecule that by itself, on its own, is polar in nature. So you have two of these polar molecules, or two permanent dipoles, that are attracted to one another. And so take water. Water is a perfect example. The oxygen-hydrogen bond, oxygen is more electronegative than hydrogen, so there's polarity in the bond. And the bent shape of the water molecule, due to the two shared pairs, the two atoms bonded to the oxygen, and the two lone pairs that exist on the oxygen, creates this permanent dipole, where your oxygen end of the molecule has a partial negative charge, while the hydrogen end of the molecule tends to take on the partial positive charge. So when you have two water molecules that are close to one another, those partial charges are going to align, and it's that, again, that electrostatic attraction, sort of like what we see with ionic compounds, but in this case, it is covalent bonding taking place, and there are partial charges, but you still get alignment of the positive to the negative, and that's where that attraction is going to take place. The second van der Waals weak force is referred to as dipole-induced dipole forces. And what occurs here is your permanent dipole is able to attract nonpolar molecules. And so the way this occurs is, again, think in terms of what happens when you have like charges close to one another. You get repulsion. So the partial charge that exists permanently on the permanent dipole will be able to either attract or repel electrons in the nonpolar molecule's electron cloud. And so when these particles are close enough to one another in proximity, because the effect of the dipole, the charge effect, is only going to be effective over a very small distance. It's analogous to if you have a magnet close to a refrigerator. The further you move that magnet away from the refrigerator door, um, the less you're going to feel that attraction. Okay, so when these molecules, the dipole is close to the nonpolar molecule, when that charge comes close enough to that cloud, depending on the orientation, whether it's the partial positive or partial negative end, it's going to distort that nonpolar molecule's charge cloud by either attracting the electrons towards it or repelling them away. And in that moment, when those molecules are close enough to one another for this distortion to occur, it is creating a dipole in that nonpolar molecule. Now, that dipole that is induced is very, very temporary. It is only there so long as the permanent dipole is close enough to create that distortion. As soon as it moves away, carried by its own kinetic energy, or what have you, that induced dipole leaves and it becomes a nonpolar molecule again. But in that moment that that dipole has been induced, it can now be attracted to the permanent dipole. Now, if all of this sounds very hazy and, well, that can't last that long, you're exactly right. It doesn't last that long. And in and of itself, it's a weak attraction. So again, it plays into this idea of these are weak forces. And the term weak is really kind of an understatement. Compared to intramolecular forces, your ionic and covalent bonding, these are much, much weaker forces. As an example, if we think about chlorine gas being dissolved in water, all right, we have a water molecule, we have a nonpolar chlorine molecule. Chlorine being diatomic, it's going to exist in two chlorine atom molecules, and being that it's the same atom bonded to itself, the electronegativity difference would be zero. So this is a perfectly nonpolar covalent molecule. When that water molecule comes close enough to that chlorine molecule, however, say the partial negative end of the oxygen end of the molecule is close to the chlorine, it will repel the electrons of chlorine's electron cloud, forcing them to the opposite end of the chlorine-chlorine bond, and in doing so create a partial positive end and a partial negative end to chlorine's charge cloud. In that same instant, you will have a force of attraction between the partial negative of the oxygen end of water and the partial positive end of the chlorine molecule that's been induced. And that's the point at which that attraction occurs. But again, as soon as those molecules move apart from one another, the oxygen leaves and the induction of that dipole moment in the chlorine molecule leaves, and it returns to what you would see in the first image, a nonpolar molecule. So we've looked at what happens when you have two polar molecules attracted to one another. We've looked at the attraction that occurs between a polar and a nonpolar molecule. So that only combination that really leaves left is nonpolar to nonpolar. And you may be asking yourself, well, if it's nonpolar, that means there's no charge there really. How can there be a force of attraction? And so as you might guess, this type of force, known as dispersion forces, is the weakest of the weak forces. Now, and stay with me here for a minute, okay? When we think about electrons moving about the nucleus, all right, oftentimes we get this picture of, like planets orbiting the sun, moving in circular orbits, and we think of them always being in the same orientation one another. But the movement of electrons about the nucleus is much more random, and so in that randomness, occasionally, the electrons may end up concentrated more at one end of the molecule. Okay, a way to think about this. All right, imagine yourself sitting at a stoplight. Okay, and you're in the turn lane. And I think we can all relate to this because we've probably all done it. You're watching the car in front of you and you see its turn signal blinking at a steady pace. And at the same time, your car's turn signal is turned on. Okay, and you hear the audible click of it. Now, as you watch the one in front of you and you listen to the clicking of your own, they come in and out of phase. All right. At first, they may be opposite one another, but then for a moment, they all come in phase. The light in front of you is blinking at the same rate that you're hearing the click of your turn signal, and then they pass out of phase again. That's what I'm describing here. with the electrons in their movement throughout the charge cloud of the nonpolar molecule. For an instant, the electrons may be aligned towards the same end of the molecule, and in that instant, you have what we refer to as a temporary dipole. And the term temporary is extremely an understatement here, because just as quickly as they're aligned, they're out of alignment again. But in that split instant, your temporary dipole can induce a dipole in a molecule that happens to be close to it. And in that split instant, that's when the attraction occurs. But again, because this is so fleeting, that's why they're so weak. So as an example, let's take our chlorine molecules again. Two nonpolar chlorine molecules. All right, and as they're moving about and as the electrons are flitting about the nuclei between those two bonded atoms, for an instant, in one of those nonpolar molecules, the electrons may come into alignment. And so we have a temporary dipole created. If in that same instant that alignment occurs and we have the temporary dipole, it's close enough to another chlorine nonpolar molecule, it can then induce that second chlorine molecule to become a dipole as well. And in that instant, you've got two dipoles, temporary as they may be, they're still dipoles. And in that instant, you can get that very weak attraction that's occurring between the partial negative and partial positive ends.